So let's start by looking at the puzzle from last time. The puzzle went like this. In a certain barber's club, every member has shaved at least one other member, no member shaved himself, and no member had been shaved but more than one member. Moreover, to make the puzzle interesting, there is somebody who has never been shaved. Question, which seems completely strange. Why would you ask such a question in a puzzle phrase like that? How many barbers are in a club like this? So this is a kind of puzzle that we use to show that there are things that may happen in the infinite domain which cannot happen in the finite. And the answer to that puzzle is that we need infinitely many barbers in order for this club to be possible. Here's how it might work. So the very first barber, barber 0, can grow a beard. For every natural number n, the barber number n will shave the barber n plus 1. So the barber with a beard shows the barber number 1. The number 1 shaves barber number 2, and so on and so forth, off to infinity. This puzzle is sometimes called the Hilbert Grand Hotel puzzle, where every guest comes and gets assigned a room, and when a new guest comes, everybody is moved to the room one number higher. So how do we even talk about sizes of infinite sets? Isn't there just one, infinite? Are there different infinities? And how do we even start asking this question? And here is where notions from our previous lectures about one-way functions, bijections, onto functions come to rescue. If we have two sets of the same size, one thing we could do with those sets is to match, like pair up elements of one with the other. So for example, if we have set with elements 1, 2, 3, we can pair them up with elements A, B, C, because 1, 2, 3 has 3 elements and A, B, C has 3 elements. And this holds for infinite sets too. We can define two infinite sets to be the same size if there is a bijection, so one-to-one and on-to function between those two sets. From first to second or from second to first, it doesn't really matter. That is, we can pair up elements of the first set with elements of the second so that everybody has one pair and nobody from either set is left behind. So the first notion that we will look at as infinities is a countable set. And a set is countable if it has as many elements as there are natural numbers. That is, we can pair up elements of our set and natural numbers. We could count elements of set A by pairing up every element with a natural number. So we will talk about first element of A, second element of A, and so on, covering all of the elements of A. And by the way, here, it doesn't really matter whether you use definition of natural number which starts with 0 or with 1. Really, the proof is exactly the same. It will be off by 1 in one case or the other. And moreover, since it's a bijection, we could make a function from our set to natural numbers or from natural numbers to our set. Both of them are going to work the same way. So let's show how to use it in practice and show something surprising. We will show that even though there seem to be more integers than natural numbers, actually there are as many integers as natural numbers because we could count integers. And here is a function that lets us do it. So let's count integers like this. So first attempt could be, you could say, okay, 0 is 0, 1 is 1, 2 is 2, and so on. Let's count all of them this way. But then if you start counting with all the positive numbers, you'll never get to negative. So we need to alternate between positive and negative. And here's how we could do it. Let's call number 0 the zeroth number. Let's call the number -1 first, number 1 second, -2 third, and so on. So we are alternating between negative, positive, and at every step we are going further and further away from the zero. Here's how to write it as a function, as a bijection. Let's define the function like this. F of x will be 2x if x is positive or 0. Otherwise, f of x will be minus 1 plus 2x. So this is where x is negative. So for example, if we plug in x equals minus 2, it will be minus of 1 plus minus 4. So it will be minus of minus 3, it will be 3, and you could see that indeed we counted minus 2 as our third number. So why is it a bijection? Well, we could show that it is both one-to-one function from integers to natural numbers and onto function. And the idea of the proof is that if we know what is the value of f of x, we can invert it and compute a value of x. And if f of x is even, then the value of x will be f of x divided by 2, and it will be a positive number. Otherwise, if it's odd, we use the formula for the negative number, and in both cases, we'll get back a different number. So onto is onto because for every natural number, we could figure out which integer, unique integer, mapped to that number. So now let's talk about the uniqueness a little bit more. So suppose there are two numbers such that f of the first number is equal f of the second number. Well, if the resulting number, let's call it y, is even, we know that the number we started with is positive, and this number is y over 2. Well, there is only one value of y over 2. So in this case, we must have started with the same number. x1 and x2 must have been the same. And similarly, you could show that if it's odd, again, you plug into the formula, there is only one number that could have given you this y. So again, only one number must have mapped to y. It's one-to-one. It's one-to-one, it's onto, it's a bijection. And by our definition of what it means for two sets to have the same size, the same cardinality, that means that integers and natural numbers are the same size. They are both countable. So here is the surprising thing about infinity. Even though there are all natural numbers inside of integers, plus a whole bunch of other numbers, negative numbers, they actually have the same cardinality. If you look at it from far enough and you squint, they kind of look the same. And in general, this is a general phenomenon. It is entirely possible, and actually it's the case, that an infinite subset of an infinite set has the same size. In particular, an infinite subset of a countable set is always countable. So integers are countable, their subset natural numbers are countable, well, this kind of by definition, but also set of all primes is countable, set of all even integers is countable, and so on and so forth.